Alright, good morning, afternoon, evening, or whenever you're watching this. This is 1.3 and 1.4. 1.3 talks about finding the average atomic mass of an element, and 1.4 deals with moles. Alright, so how do you find what is the mass of a element, and how do you find it? Well, you use a mass spectrometer, and it measures the mass of each isotope that is present in the element, because remember, elements are averages, and it tells you how much of that isotope is present. So for example, here's zirconium. Its molar mass, average molar mass, is 91.3 grams per mole. And you can see there are 5 samples of zirconium isotopes. That means there's 5 isotopes, one at 90, that's a little above 50%, 91, 92, there's an isotope at 94, an isotope at 96. So those isotopes will equal 100% of that sample. So how does a mass spec work? Basically, you have a sample that ionizes, so it has to be a vapor, and it accelerates through a vacuum, and it has a magnet, and it deflects it either a positive or negative way, because an ion can be positive or negative, and that deflection gets detected, and that will determine its weight. Here's another sample. It's magnesium. You see the majority of it, it's 79% at 24. That means its mass is 24. You have one at 25, 10%, and a little higher, 11%, 26. So how can we find the average relative atomic mass using this? So it's pretty basic, like finding your class average of a class. So what are the isotopes? We have magnesium 24, magnesium 25, and magnesium 26. They're all magnesium, so therefore they all have 12 in the bottom left-hand corner, because those are the number of protons for magnesium. If that number changed, it wouldn't be magnesium anymore. So finding the mass from the data. So 79% is isotope 1, and it's of a mass of 24. So that means you take 79% of 24. So you just got to make sure you convert that to decimal, move it over 2 spots, or divide by 100, and you get 18.96. Isotope 2, 10% of 25, that's 2.5. Isotope 3 is 11% of 26, so 2.86. Add up all 3 together, you get 24.32. Sig figs, you can only go to the tenths, because the 2.5 is the least precise, so you get 24.3 grams per mole. Alright, check it out. Make sure you know how to do these 2 problems. If not, you can always ask questions in class. Page 4, number 2, you want to find the heaviest isotope of germanium. And then 2b, or not 2b, use the abundance percent of each isotope, and you want to calculate just like we just did for magnesium. So for 2a, the heaviest you should see on your chart is 76, so germanium 76, and then you have 5 isotopes of germanium, 20.6%, 27.4%, 7.7%, 36.7%, and 7.6%. So you do all the same math, multiply all up, then add them all together, and you should get 72.5 grams per mole. So make sure you know how to do that. Simple math of multiplying and adding. Alright, 1.4, moly. Yes, back to moles. So we know atoms are very tiny. We can't see them. We know they're there because of experimentation. So we still need a measure. So how we measure these things? And that's what moles come into. So we know it's very, very small. So we need something that can use that scale to help us with that daunting small value. So we come up with a mole. Actually, oh, can't give it away. So what is that number that relates small things like atoms, particles, electrons, formula units? And if you're guessing in your head and you are thinking, oh man, I really know it. I think it's, yes, it is Avogadro's number. So if you forget Avogadro's number, here it is. 6.0221415 times 10 to the 23. Obviously, you don't need to know that many sig figs. 6.022 is fine. 4 sig figs times 10 to the 23. So, how does that number relate? Well, remember, atoms are small. So if you have a mole of atoms, how many atoms are there? You have lots and lots of atoms. And that's where Avogadro's number comes in. 6.022 times 10 to the 23 atoms. Just like if you had a dozen cookies, dozen means 12. A mole equals 6.02 times 10 to the 23. If you have a mole of cookies, that's a lot of cookies. 6.022 times 10 to the 23 cookies. But we're not dealing with cookies, we're dealing with science. Molecules. 6.022 times 10 to the 23 molecules. If you have a mole of particles, yes, same value. 6.022 times 10 to the 23 particles. Mole of formula units. Formula units are ionic compounds, and that's the same value, 6.022 times 10 to the 23 formula units. And mole of electrons, again, same value, 6.02 times 10 to the 23 electrons. So if you're dealing with a mole of anything, it doesn't have to be these 5 things. It would be a mole of computers. You would have 6.022 times 10 to the 23 computers. Quick practice. Again, mole of sodium atoms, Avogadro's number. Mole of fluorine atoms, same thing. Doesn't matter what element you have. It doesn't matter what substance you have. It's always going to give you the same value. Mole of sodium chloride, 6.02 times 10 to the 3 molecules. Now, why use molecules this time? Well, sodium chloride isn't an atom. It's made up of atoms. It's a molecule. It's a formula unit. You can use formula units here, molecules. You just can't use atoms because sodium chloride is not an atom. Mass of whatever. So a mass of sodium. Go to your handy dandy periodic table. You would have 23 grams per mole. Fluorine's around 19. And then sodium chloride, again, remember from last section, add up sodium, add up chlorine on the periodic table, you get 58.5 grams per mole. More review of Avogadro's number. So if you have a mole of sodium, 6.02 times 10 to the 23 atoms of sodium. If you have a mole of sodium chloride, same thing. Avogadro's number, 6.02 times 10 to the 23 sodium chloride units. Now here's a little tricky. So sodium chloride is made up of 2 ions, a sodium ion and a chlorine ion. So sodium is plus because it loses 1 electron. Chlorine is negative because it gains that 1 electron. So how many ions are present in a mole of sodium chloride? If you said Avogadro's number, you are correct. If you did not, you're wrong. But that's why we're reviewing. 6.02 times 10 to the 23. Now why? That's a good question. Now, if you look at the sodium chloride molecule, there's 1 sodium for 1 chlorine in the molecule. So, it's a 1-to-1 ratio. So if you have 6.02 times 10 to the 23 molecules, you would have 6.02 times 10 to the 23 ions. And the same thing for chlorine. It's a 1-to-1 ratio. Now, if you're dealing with a non-1-to-1 ratio, then you do have to do some multiplication of 2 or 3, depending on what ions are present. Quick review of diatomic elements. chlorine, fluorine, oxygen, nitrogen, iodine, hydrogen. You want to make sure you remember a molecule is made up of atoms. In this case, diatomic meaning 2, and an atom is just 1. So if you have a mole of chlorine atoms, you would have 6.02 times 10 to the 23 atoms. Now, if you have a mole of chlorine molecules, it's a little different because chlorine is diatomic. If you said double, you are correct. You double the amount of Avogadro's number because it's a 2-to-1 ratio. Here's the quick dimensional analysis of it. You have 1 mole of chlorine molecule, Cl2, and in 1 mole you will have 6.02 times 10 to the 23 molecules because it's not an atom, it's a molecule, it's made up of atoms. And in 1 molecule of chlorine you have 2 atoms. So if this was like ozone, which is O3, it would be 3 atoms for 1 molecule. If you had sulfur, S8, it would be 8 atoms per molecule. So quick flowchart of Molar. Remember Molar, you'll get a diagram like this in class, but a little more fun. So everything goes to Molar. So if you have something that's small, like atoms, particles, formula units, you would use Avogadro's number, like here. If you have mass, grams, you would use their molar mass. And if you have a gas, you would use STP, which we'll get to later. So here's a quick overview again. Atoms to moles use 6.02 times 10 to the 23. If you have moles to mass or mass to moles, you use their molar mass. So you gotta remember something small, Avogadro, mass, molar mass. All right, here's some examples we'll do. You have 10.7 grams of sulfur atoms, and you gotta find moles. So you have grams, that's a mass. So you gotta think molar mass. So your given always starts in dimensional analysis in the top left-hand corner. 10.7 grams of sulfur. Then you need to find the molar mass of sulfur. So you go to the periodic table, 32.066 grams, and 1 mole. Grams cancel out, and you are done. 0.335 moles of sulfur. So that's just converting grams to moles. Now, a little more difficult because now you're dealing with a sulfur molecule, which is S8, so the molar mass is going to be a little different. Still, your given is 64.2 grams. Now you need the molar mass of S8. So you just take the molar mass you just found, 32 grams, and you gotta multiply it by 8. You get 256.528 grams. And that's 1 mole. Grams cancel out like before. Do a little division. You got a 1/4 mole of S8. Alright, now we're dealing with an ionic compound, iron 3 nitrate. And you have 60.45 grams of it. So you're given, still top left-hand corner, molar mass, you gotta look up iron, you gotta look up nitrogen multiplied by 3, you gotta look up oxygen multiplied by 9, because that 3 gets distributed to both atoms. And you get 241.86, and that's 1 mole. Grams cancel out, and do a division, you get 0.250 moles of iron 3 nitrate. Alright, calculate the atoms in 7.10 grams of chlorine atoms. So, a little more work because it's an extra step, but you always start with your given, which is 7.19 grams, and since you're dealing with grams, you gotta find the molar mass. Now it's chlorine atoms, not a molecule. Remember, molecule is diatomic, an atom is just an atom. So you look up chlorine, which is 35.45 grams. You need 1 mole. Grams cancel out. So now we're in mole land. Great. Yay, moles. We're having fun. Like, man, I really want to get to Avogadroville. So that means you need to use Avogadro's number. Since moles is your unit, you need moles on the bottom. And you know from Avogadro's number, it's 6.02 times 10 to the 23 atoms of chlorine. So moles cancel out because they're diagonal from each other. And you're left with atoms. Do a little multiplication, do a little division, and you get 1.21 times 10 to the 23 atoms of chlorine. Alright, here is your homework assignment. Calculate the mass of the following. You have 0.20 moles of carbon dioxide, CO2, 0.050 moles of sodium carbonate, Na2CO3, and 5 moles of iron 2 hydroxide, FeOH2. Here are the answers, so you can check your work. But to get your credit, you need to make sure you show your dimensional analysis. You're going to have to find the molar masses of your molecules, and